All right, so I've got a little video going here about how to deal with functions that don't have horizontal asymptotes. And we're going to notice that, like we put in our notes last time, this happens when our numerator, got a nice pen over here, so our numerator degree is greater than the denominator. We should really think about this as far as like what's going to happen when we put in really big numbers, right? So as we put in really big numbers, this x squared is going to exponentially increase and the denominator is going to move much slower. So if I put in positive values, right, and really if we put in anything up top, but our denominator is going to play with positive, negative. So if I put in any positive values, the whole fraction will be positive and everything's going to go to positive infinity. X squared is going to get huge. If we put in negative numbers, our denominator is still going to be the biggest, our numerator is still going to be the biggest, but our denominator would be negative. So as we go to negative infinity, our graph will just keep getting lower and lower. And if we're not sure about seeing that right now, we can use another form that'll help us out. And that's also how we're going to find if we have any asymptote at all. So we're going to use synthetic or long division to rewrite this function as like a constant or an equation with a proper fraction. So with a fraction where the numerator is less than the denominator. So take a minute and do your synthetic or long division, and I'm just going to skip ahead here and write my function with that remainder. So at the end, you guys see here I have this function equals x minus 1 plus 1 over x plus 1. So if we look at that and we think about as our function goes to positive infinity, right? When I put in really big numbers, this fraction over here is going to get tiny. If I put in huge numbers, that fraction is not going to make a difference at all, and our function is going to go towards this guy, x minus 1. All right, so as x gets bigger and bigger, my graph's just going to keep getting bigger and bigger, and it'll actually follow x minus 1, so we call that the slant asymptote or the end behavior asymptote. And our equation would be that y equals x minus 1. So I think I'm going to throw that on the graph. There we go, got a couple points. All right, so that's really our big difference now. When our numerator degree is greater than the denominator, we're going to have some kind of end behavior asymptote. So take a minute and do your analysis just like we normally would. So you can write out your vertical asymptote, your intercepts. Oh, I just skipped ahead a lot. And then we want to determine if it crosses the slant. Maybe I'll do that with you first, or you could pause and try it out. But just like we did before, if we had a horizontal and we wanted to check if we crossed it, we would set the horizontal asymptote equal to the function. So I'm going to do the same thing. I'm going to set my slant asymptote, which is x minus 1, equal to our function. And just notice that I'm going to use, I already circled and drew an arrow, I'm going to use this function right here. It's the same as my original that they gave us, but watch what happens when we throw it down here to go through. So if I set it equal to this kind of fraction plus our slant form, and I start to simplify, I can cross out those x minus 1s, I get 0 equals our fraction, really quick to solve. Multiply by the denominator, 0 equals 1, so for us, means we're not crossing the slant. All right, so again, that's the new stuff on this graph. You guys could write in everything else, and I'll show it on here. Right, our intercept, only 0, 0, and check out this numerator up top. It's x squared, so that means my multiplicity is going to be 2. So I'll throw that on the graph with our asymptote. And since our multiplicity is 2 at 0, we're going to bounce right back off and head up towards that slant asymptote. Now remember, for this bottom zone down here, you can either check a point, or we can think about our multiplicity rules so that our denominator, x plus 1, really messy, is a degree 1, so my sign's going to change from the top of this to the bottom. Get rid of all this stuff that I just added in there and draw in that last piece. And that's all we need for this function.